go to the cloud. Okay, hello everyone. Let us start. So let me remind you that last time we met, we discussed harmonic functions. Can you hear me, people? Not people in this room, but the people in the people that are not in the audience, but people on. Can you hear me? Can you see the? So just a minute ago, we had the connection was perfect. What happened? Okay. Stop. Good to see you as well. But let's see. We have some Zoom user. Just a minute ago it worked, yeah. Okay. Now. Okay. And okay, so people in the virtual part of the world, can you see me?
Yes.
Can you hear me and can you see the iPad?
Yes.
Just no response. Is anyone actually there?
Maybe we can hear them.
So there are 6 participants online. Can any one of you write in chat that you can? Okay, yes, someone wrote in chat. אנחנו לא שומעים אותנו. אתם לא שומעים אותנו, אוקיי? But האם אתם שומעים אותי? כן, אוקיי, אחלה. And...
אז למה אנחנו לא שומעים? אולי צריך לחבר פה משהו? איפה כן? כן לא מדי טעם.
לא, זה פעם מקודם. אני חושב שזה בגלל שאתה משתף דרך האייפד ולא דרך המחשב.
טוב, אני לא אגע פה בכלום, כי פעם קודמת זה בכלל לא עבד. אוקיי, אז... אם אפשר לבקש.
אני מנסה גם להתחבר מהמחשב, אולי אני יודע. אז נעשה פה ניסויים. תראה, אם יש לך, תשחק עם זה, מה להתחבר למחשב? מה הכוונה?
חשבתי אולי, אבל רק כאילו לשתף מהמחשב.
לא, אני תמיד עבדתי בדרך הזאת, ותמיד היה אפשר לשמוע. אני, כנראה שהמייקרופון.
זה לא על הסטייק או משהו, נכון?
איך אני יודע? בוא נבדוק. So כרגע, the mute all, so we need to enable participants to security. Allow participants to unmute themselves. Yes, so they're supposed to be.
נראה לי אבל זה ב-V, זה מסומן. עכשיו זה כאילו עשינו שהם לא יכולים.
אז תעשה שוב. People, try to unmute yourself and speak.
אני מבקש מהאנשים לעשות unmute.
ניסיון?
כן, מצוין.
אוקיי.
אחלה. אז הכל עובד. טוב, חוזרים שוב לזה. אוקיי. And here we go again. Yo. Okay. It's really to develop patience. It really helps to develop patience.
טוב, אתה צריך להחליק מהפינה למעלה.
מאיזה פינה למעלה? יש הרבה פינות ואני, הנה, החלקתי. פעם החלקתי. כן. כן. אוקיי, והטכנולוגיה הזאת. As I remind you last time, so reminder. So if the function f of z, which has a real and imaginary part, is an analytic function, then the function u and v are harmonics. So what it means that each of them satisfies Laplace equation. Okay, so now let's play with this idea a little bit and see how it works. So example number 1, find harmonic function. Okay, thank you. And these are not the conditions. This is what follows from the statement. So if you know that function f is analytic, then necessarily the following two conditions hold. Okay, so now the problem, example number 1, find a harmonic function u of x and y on the complex plane, xy, if the function u satisfies, or that satisfies the boundary condition. U of x is equal to x on the real axis. So what this problem is about, you have a plane x and y. You can look at it as a complex plane, or you just can look at it as a normal plane. It's up to you. And then there's a statement that on the real axis, on the x-axis, we know that the function u of x is equal to x. And what we need to find is the function u of x and y away from the real axis. And what we know that function u is harmonic function. So we know that it satisfies, Laplace equation. So it's an equation from the differential equation course, as I promised. Now you study differential equations, so you know that if you're given a differential equation and the boundary condition everywhere, you should be able to solve this equation and find this function, right?
Yeah.
So what is the solution?
If we just have another linear component of y that is imaginary. For example, x plus I y would satisfy this equation. Because the second derivative of x of u with respect to x is 0, and the second derivative of u with respect to y is also 0.
Maybe x squared and iy squared. It will give you the result.
Well, first of all, let us notice that function u of x and y is a real function. By construction, we're solving.
Okay, so just, yeah, plus cy then, not iy, just any c.
Okay. Okay, so let's see how it works from the complex analysis perspective. So it's an absolutely trivial example. All of you solved it some of you solved it just in 1 sec. So let us see how it works from complex analysis. Okay, so how can I approach the same problem if I know complex analysis? And if we go back 1 slide and look at the theorem we used, so if we're able to construct analytic function on the complex plane such that its real part is known on the real axis, then we know the function everywhere. So can we construct a function f of z, which is by construction is equal to this, such that for z belonging to the real axis, f of z is equal to u of x. Oops. And we probably will have to go through all this procedure again.
דימה, כשאתה מדבר בעצם על זה שצריכה להיות לך פונקציה f של z, נגיד u של... אז בעצם הפונקציה שמקודם הצעתי לך, x בריבוע ועוד y בריבוע, היא מתאימה, היא f של z שמתאימה לך, לא?
אוקיי, בוא נבדוק את זה. פונקציה f של z שזה x בריבוע ועוד y בריבוע. זאת הפונקציה?
iy בריבוע.
iy בריבוע. האם הפונקציה הזאת מתאימה? לדעתכם.
היא לא שווה ל-x כאשר y שווה ל-0. כאילו, צריך את הבאונטי קונדישן.
אז אם אנחנו on the real axis, which means y equal to 0, הפונקציה הזאת היא x בריבוע. והיא שונה מ-x.
אז אתה רוצה בעצם פונקציה שגם מקיימת את תנאי השפה שלך.
בדיוק.
הבנתי.
אז לכן הפונקציה הזאת לא מתאימה.
אז אולי הצמודה ההרמונית של יהיו כאילו תתאים פה?
אז תיקח את x ועוד iy בריבוע. לא, בעצם לא, זה לא יעזור.
Any more educated guesses?
זה למרות את הצמודה ההרמונית של יהיו.
So just say the function.
מינוס יהיו בעצם.
But u is something that I'm looking for.
לא מה ש...
Oh, we're not continuing from the u that we've found?
No, I know function u on the real axis. I want to find u everywhere. That's my problem.
Okay.
I only know it's on the real axis. And I want to write an analytic function that is equal to this function on the real axis. And I claim that if I found an analytic function that matches this function on the real axis, I found it everywhere. So what analytic function means? What do we mean by
the Cauchy Riemann?
Right, but if I write an analytic function of z, what it means?
U plus IV. Or like, I'm not understanding what you...
Okay, fine, fair enough. Okay, so can you invent a function f of z, which is an analytic function of z, such that on the real axis it agrees with the function x?
Just x plus iy? Or
X plus iy. In other words, this is just z.
Yeah, just z.
So if f of z equals z is an analytic function. Yes, good. On the real axis, f of z equal x plus I0 is equal to x. Does it match with my function u?
Yes.
So then it means that, my function f of z being equal z, being equal to x plus Iy. So then x is a real, so x is just u of x and y is just v of x and y. And we found two functions, u of x and y equal x, and v of x and y equal v, or equal y, sorry. And these two functions by construction satisfy our harmonic equation. So we found function u of x and y such that on the real axis it matches with the known function and it's harmonic everywhere. That was a trivial example. So let's consider a slightly less trivial example. Example 2, the same problem, but the function u of x and y on the real axis is equal to x squared. Can we find a harmonic function u of x and y everywhere on the plane?
X squared plus IY squared.
Minus y squared.
So u of x and y, you propose to be what?
Because remember, it has to satisfy Laplace. So
right.
the second
So
derivative by x,
yes.
so minus y squared.
It's a wrong logic. You don't need to, that's the whole point. You don't need to remember that it must satisfy Laplace. You want to write a function which is an analytic function of z. And by construction, it would satisfy Laplace equation. So can you think about some function f of z such that its real part, v of x and y? Yes, exactly. So let's think about the function f of z equals z squared. So if you want to write it in terms of x and y, this is x plus Iy squared. That will be x squared minus y squared plus 2ixy. Now, I claim that these two things must satisfy Laplace equation by construction because the function f of z equals z squared is analytic. So how do I see it? Let us check. So this will be u of x and y, and this will be v of x and y. So first of all, does u of x and y matches the function x squared on the real axis?
Yeah.
Yes.
Yes.
Okay, now how about Laplace equation? That will come out automatically. So let's just check. Dx squared u plus dy squared u. It's equal dx squared acting on x squared minus u squared plus dy squared acting on x squared minus y squared. So the first term gives me 2, the second term gives me minus 2, and altogether it's 0. So I found the function x squared minus y squared, which is harmonic, and it's equal to a given function on the real axis.
Then how did you make the educated guess of z squared?
Because function z squared is equal to x squared on the real axis.
Yes, but ultimately it was previous knowledge or some sort of educated guess, because it's just like saying it's just like the harmonic differential equation. We're not solving it. We're just knowing from previous knowledge that cosine and sine satisfy the equation. Then I'm asking you, is it just previous knowledge and you just know this, or is there a pattern? Because the previous one you wanted, for the previous example, you wanted the function to equal to x on the real axis.
So I took
z. And then you just said that the function was z.
Right.
And now you wanted x squared and you guessed z squared.
Right. And if it would be x in the power n, I would have guessed z in the power n.
All right.
Okay, so example number 3. See, it's also trivial example, but I just want to make sure that we understand. So the same problem, the same equation, but on the imaginary axis this time. And the function u at x equals 0 and y is equal to y. What is the harmonic continuation? What is the harmonic continuation? Or what is the harmonic function u of x and y that on the imaginary axis is equal to y? So what should be analytic function f of z such that its real part is equal to y on the imaginary axis? Is it z?
Is it minus I times Z?
Minus I times z, yes. It's a minus I times z because if I put it here, x plus iy, I get minus ix plus y. And this is indeed the real part of this function. Therefore, it's obviously harmonic, and this is my function. It is just the real part of minus iz. Okay, so let's make life slightly more interesting. This time, let us choose a different boundary. Let's take a unit circle as a boundary. Minus I, 1, and minus 1. And the same equation. And we know that on the unit circle, we can define an angle theta. And as a function of angle, the harmonic function is equal, I don't know, cosine 3 theta. And we ask, what is this function u? What is the harmonic function u on the complex plane or on the plane? If we know it's on the boundary of the unit circle. Of course, you can write a differential equation in the spherical coordinates and solve it with this boundary condition, or you can write it from analytic continuation. So how do we find a function by analytic continuation for this problem? What would be function f of z? Okay, u of z would be real part of z in the power 3. And this is equal to real of x plus iy cubed, which is equal to x cubed minus 3xy. And since we're already here, v of x and y will be imaginary part of the same object. And this will be 3x squared y minus y cubed, sorry. Let us check that these functions are indeed harmonic. So d2 dx squared u plus dy squared u is equal to 6x minus 6x is equal to 0. And d squared v plus dv is equal to 6y minus 6y equal to 0. So you see that in one line, I'm getting a solution of this differential equation just using the boundary condition and analyticity. Okay, let us make life a little bit more interesting. The same problem, but the boundary condition is slightly more interesting. So again, on the real axis. And I want function u on the real axis to satisfy the following boundary condition: to be 1 for x greater than 0 and to be 0 for x less than 0. Okay, so I want to find a harmonic function with these boundary conditions. How do I solve this problem? Any ideas? What function should we use that will mimic this behavior? Any ideas? Do you know any function that jumps?
A sine or
Sine is a great example, but sine is a function of real variable. What is a counterpart of sine for complex analysis? No. Yes, but what is this function in complex analysis? Something that you know as a theta function in real analysis has a natural counterpart in complex analysis, and you all know it. Lan, of course. Yes, correct. So lan or an argument of lan. So let's go there. So let's define theta, an angle which is an argument of z. So obviously we know that if you take a function lan of z, it will be lan of absolute value of z plus I theta. So if we take lan over z and divided by pi, we will get 1 over pi lan absolute value of z plus I theta divided by pi. So if we take imaginary part of 1 over pi lan z, that on the real axis, it will be theta over pi, and this will be precisely 0 or 1, depending on the theta. So on the real axis, we have only two options. So we either here or there, and then theta is either 0 or pi. So it means that u of x and y is imaginary part of 1 over pi logarithm of z. And this is a function that satisfies boundary condition and is analytic and harmonic. Okay, so now these were examples. So now let's try to see what we actually did in these examples. And what we did in all these examples was actually what mathematicians would call analytic continuation. So an analytic continuation. We did it without defining it, and now I'm doing a proper definition. So suppose there is a complex plane, and there are two regions in the complex plane, say D1 and D2. These regions may look like this. So in some of the examples, region D1 was an upper half of the complex plane, and D2 was the lower part of the complex plane. And some of the examples, it was a circle, and the region D2 was the interior of the unit circle, and D1 was the exterior of the unit circle. These were the examples, but in general, there are two regions on the complex plane with a common boundary. So there is a common boundary between these two regions, but no overlap. And there are functions. There are function f1 and functions f2, f1 is analytic in D1, and f2 is an analytic function in D2. Okay, so there are analytic function f1 in D1 and analytic function f2 in D2. Now, if it happens that f1 of z is equal to f0, I called it, sorry, f2, okay, then f2 of z for all the points on the boundary, let's call boundary, let's give a boundary name, say gamma, it's the boundary. So for all points on the boundary, then we can define function f of z that is f1 of z for z belonging to D1, f2 of z for z belonging to D2, and it's equal to f1 of z, which is equal to f2 of z for z belonging to the boundary. So in this case, we say that f1 is an analytic continuation of f2 to D1, or f2 is analytic continuation of f1 to D1. And the point is that we know function in one domain, say D1, and we don't know the function outside of this domain. But if we manage to find the function that it's equal, so function f1 is analytic inside D1, and we don't know the function in D2, but we've managed to find a function which is continuous and equal to the function f1 on the boundary, then we will call function f2 an analytic continuation of the function f1 to D2. We can solve a reverse problem if we know f2, we can analytically continue it in the domain D1. Okay, simple example. Okay, consider function f1 of z, which is equal to 1 plus z squared plus zn plus. This would be an infinite series. And I define this function as an infinite series on the complex plane, where this series converges.
For z that is smaller than 1.
For z smaller than 1. Is this function analytic as a function of z?
Yes.
Yes. So from the point of view of the previous statement, we have a domain which is just a unit circle on the complex plane, where we define, so let's call this domain D1, where we have defined function f1 of z, and it's analytic. I want to analytically continue this function to the domain D2, which is outside of the unit circle. How do I do it? If I naively just look at this expression and take and substitute Z to be a point outside of unit circle, this series will diverge and make no sense. But I want to define this function f1 of Z outside of the unit circle in a way of analytic continuation. So exactly the way I just specified. How do I do it?
Z to the power to the negative powers. 1 over Z, 1 over Z squared, 1 over Z, and so on.
So you want to define f2 of Z being Z in the power minus 1 plus Z in the power minus 2. Will this function match all the boundary?
They both sort of converge.
But they converge to the same value.
To the same value, but they're both exploding to infinity. But yeah, or am I missing something?
No, it's
when Z is equal 1.
It's almost correct. I think it may be even correct. So let me show how it works. So let me look at this function f1 of Z, and let me sum this series where I can sum it, where it converges. What is this series when it converges? Can we sum the entire series?
1 over 1 minus Z.
Correct. Do we agree? Now this expression 1 minus 1 over Z is defined outside of the unit circle.
Take Z to be 1 over Z.
So the expression, this expression 1 over 1 minus Z is defined outside of the unit circle.
Yes, it is, but it doesn't. It is also not defined on the boundary. I'm not sure.
It's defined on the perfectly defined on the boundary except one singular point, which is Z equal 1. Everywhere else, it's perfectly defined. And by construction matches the function f1 of Z. Now, if you want to compare it with the expression that you proposed, let's look at this. Let's look at this thing. So for Z greater than 1, let us check. So let us write it as Z 1 over Z minus 1. Agreed? Now this I can write as minus 1 over Z, 1 over 1 minus 1 over Z. Now, since Z is outside of the unit circle, its absolute value is larger than 1. So I can expand it in 1 over Z. And this will be equal to minus 1 over Z plus 1 over Z squared plus 1 over Z cubed plus. So it's equal to what you have proposed with up to a total sign. So what did we do? We had an infinite series that was defined inside the unit circle. We summed this infinite series and we got that the value of the function it's equal to 1 minus 1 over 1 minus Z. And we analytically continued this function beyond the boundary of the unit circle. And this thing, 1 over 1 minus Z, is perfectly defined on the complex plane everywhere. Okay. a little bit less trivial example. So that was an absolutely trivial example, right? Far less trivial example is called Riemann Zeta function. So one of the most famous functions in mathematics, it's sum over all integer numbers, 1 over n in the power s. So it's a function of s, where s is the power at which you take integers. Now, if you look at this function and try to compute it, say, for s equals 0, then we will get a series of that looks like 1 over n in the power 0, which is just 1 plus 1 plus 1 plus, and all this is equal to minus 1/2. So
Right.
if you use this expression as a definition, then this result looks extremely strange, because we end up having a series that obviously is not converging, and then you open any table of values for zeta function, and then you see that this sum of ones is equal to minus 1/2. And then the question is how come? Yeah. So the statement is that you should consider these definitions of Riemann zeta function as in the following sense, exactly in the sense of analytic continuation. So you first of all allowed to use this equation as a definition of the Riemann function only when this series is converging. And this series converges only if real part of S is greater than 1. Right? So in this case, this series converges, so there is absolutely no problem of computing it and using this series as a definition. But if S is smaller than 1, if the real part of S is smaller than 1, then this series does not converge. So the way we understand this function is that we understand it as a function of the complex variable S. So complex variable S has a real part and imaginary part. So we compute this function here, where real part is greater than 1. And then we analytically continue Riemann zeta function from values where S is greater than 1 to the values where S is smaller than 1. So let me show you how we do it. So let's consider our Riemann function as a function of a complex variable Z. I will write it. I will separate odd and even integers. And I'm only using this series in the part for the values of Z where this series converges. Now, here, this part changes sign. So I can write it separately. Plus 2 over 2 in the power Z, sum n from 1 to infinity, 1 over n in the power Z. But this guy is by construction, is a Riemann function itself. So do I have here is a sum n running from 1 to infinity, minus 1 n in the power n minus 1 n in the power z plus 2 over 2 in the power z psi of z. So now, and this is the whole thing is psi of z. So now it means that psi of z times 1 minus 2 over 2 in the power z is equal to sum over n from 1 to infinity minus 1 n minus 1 n in the power z. And this yields n in the power z is equal to 1 over 1 minus 2 1 minus z sum over n from 1 to infinity minus 1 in the power n minus 1 n in the power z. Now, since here this is the infinite series with the changing signs, this thing has a different radius of convergence. It converges for real z greater than 0, as opposed to previous series that was converging for the real value of z greater than 1. And now I can look this series which converges and look at the limit z goes to 0 of minus 1 and minus 1 n in the power z sum n from 1 to infinity, and show that this approaches 1. And therefore, n of psi approaches to 1 over 1 minus 2. It's equal to sorry, 1/2. Approaches to minus 1/2. Okay. That was
למה אמרת ש-XIZ כשהוא קרוב ל-1 חלקי 1 פחות 2 שווה למינוס חצי, לא הבנתי. כאילו לא הבנתי האחרון.
Sorry. So we have 1 minus, sorry, I was too fast, times limit z approaches to 0, sum and run from 1 to infinity, minus 1 in the power n minus 1 n in the power z. This will be equal to minus 1. This has a perfectly well-defined limit of convergence. This will approach 1/2, and altogether will be equal to minus 1/2. And this you just need to take this series and analyze. How do we do that? Well, that's another exercise we can discuss how we do it, but let's just believe it for a second. Okay. Okay. So that was an idea of continuing functions, and what we did so far was continuing analytic function of single valued function. Now, next level of complexity is to discuss what happens if we want to analytically continue multi-valued function. So let us be very specific and consider a simple example. Let us consider, for example, function f of z being square root of z. This is the simplest multi-valued function that I know. So how did we understand square root function up till now? What was our understanding of this function on the complex plane? As a multivariate function. How many possible values did we have? Right. So how did we define it? Okay, so let's say that z is equal to the absolute value of z times in the power I theta. No, so this is z before. Now let's discuss square root of z. So what are the two branches? So this is a multivariate function. So this, the way we wrote it here, it's a multivariate function. So let's define two branches.
N could be 0 or 1.
So let's define branch number 1 will be and the branch number 2 okay, so what we did, we had a complex plane. And then on the complex plane, we had a cut somewhere. If we could have put this cut here or in any other direction. And then we say that in all points where I don't cross the cut, I can pick a branch of this function. It will be analytic single valued function. I can either use the first branch of this function or the second branch of this function. That's my choice. So the function square root of z was not analytic because it was multivalued. However, a branch of this function, which is either first branch or the second branch, is an analytic function on the complex plane if the points on the cut are excluded. That was what we have learned about a square root of z. Now I'm going to propose you a different way to look at this function. And I'm going to propose you the way to look at this function as an analytic function, the way which was suggested by Riemann. So obviously the function square root of z is not an analytic function on the complex plane. There's no way around it. So what Riemann proposed it, that instead of looking at the function square root of z on the complex plane, let us look at it on a different manifold. It's a continuation of Riemann's sphere way of thinking, but for more complicated functions than just polynomials. So how Riemann proposed to do it? He says, okay, since we have two branches of this function square root of z, let us make two copies of the complex plane. So let us, instead of one complex plane, let us draw two copies of the complex plane, and let us choose, and let's make cuts in both complex plane, well, let's say along the positive real axis. That should not matter, but that's the easiest way for me to explain. Let us choose a cut in the, so this will be a domain D0, This is the domain D1, domain of analytic continuation. Okay, so let us decide that we choose the first branch of square root on the domain D0. So what is the first? What is the branch number 1? It's square root of the absolute value in the power 1/2 times e in the power I theta over 2. So here, that's how we understand square root of z on the domain D0. So we just attribute the values of the first branch that we had formally on the complex plane to the function on the sheet number 1. Similarly, at D1, we will consider this function, but take the second branch. Okay, so far we have two separate branches of the complex plane with a branch cut. And now we're gonna do the following exercise, and it would be very hard for me to draw. So imagine when I say there is a cut on the complex plane, I really take a scissors and cut the complex plane. So, well, I don't have scissors here, but imagine that I have a sheet of complex plane with a half of it cut. So it will schematically, I'll try to draw, it will schematically look like this. It will be a three-dimensional. It will be a three-dimensional cut on the plane. So this will be the upper part of this cut. This will be the lower part of this cut. Yeah, so points are not getting lost. I'm just cutting along there.
Are you gonna attach them like that?
Yes, I'm gonna attach them like that. That's it. That's exactly. And now let me explain very carefully how I'm gonna attach them. So suppose I have a point on the here. Let me take a point here, essentially on the edge from below. That call me this point A. So on the real axis, it was a point somewhere here, just there on the edge, on this edge of this thing. What is the value of the first branch of this square root on this sheet?
What is the value of what? Of that?
Of this function at this point A. So for the point A, the value of theta is equal to 2 pi. So the first branch has the value of square root of z times e in the power I pi, which is -1. So it's altogether minus square root. Now, if I look on the second branch, second branch is defined here. I claim that at this point, it has precisely the same value because of the extra pi there. Therefore, I glue this point A to that point A. And when I glue it, it means that my function here continuously being continued on to there. So I'm moving from here, I'm moving to there, I came to there, and I'm continuing from to here. I keep moving, and I came to that point. Let me call this point B. So what is the value of the second branch at the point B? At the point B, point B, the second branch has a value 1/2 times e in the power pi I plus 1 times 2 pi. So it will be e in the power 2 pi I will be 1. So it means that the value of B will match the value here. And therefore, I glue B to B. Now, I'm not capable of drawing it, but if you will look Riemann surface for square root on the internet, you will find you will find a drawing of self-intersecting surface, which I just explained as a mathematical abstraction. And this thing is called, it has a name, it is called Riemann surface for the function square root of z. Now, this Riemann surface, it does not look like a sphere. This Riemann function looks like two sheets glued together. I can draw it. I can draw it by hands, but that's something that you could realize if you have scissors and two sheets of paper and a glue.
You can also say that if you take a paper and do a cut to the paper, then one paper into other paper.
Yes, and then what did we get? What is the advantage of this? Now on this Riemann surface, function square root of z is analytic and 1 to 1. So if you give a point on this construction, on this Riemann surface of square root of z, on this particular Riemann surface, that you know exactly what value the function square root of z has. So we have analytically continued function square root of z. Now it has no longer any branches. It's uniquely defined as 1-to-1 function, single value function on this Riemann surface. Now I just did it as an example for the case of square root of z, but in fact you can take any function z in the power 1 over n, for example, and repeat the same argument. And this time you will need to have n replicas of the complex plane and glue them together 1 to 1. So the picture would be, if you've seen the parking lot, that multi-level parking lots in United States, if you want to park in the downtown, so you come, and then the ceiling of one floor is the bottom of the upper floor. So it looks like this.
Helix?
Yes, exactly. So that's how the Riemann surface of for the function 1 z in the power 1 over n, it will be n floor parking lot. And if you will take a logarithm, that in this case, this tower will be infinitely high. But these would be Riemann surfaces. These would be Riemann surfaces of multivariate function. And this is one of the major objects in complex analysis that is extremely important for other branches of mathematics. So in here comes your first bonus assignment that I promised long time ago. Now we are ready. So, so that's your assignment. You need to draw Riemann surface for your choice of analytic function. So you need to pick up a function, couple of functions that you like. It should be different from functions everybody else picks. So I don't want to get the same set of solved examples from everyone. So pick the function that you like, couple of functions, and draw Riemann surfaces. Draw and play with Riemann surfaces. There are many applications, in particular in Mathematica you can draw. There's a standard command that draws Riemann surface. You you define the function and you ask to draw a Riemann surface, and it just in 1 sec draws a Riemann surface. And you can take a Riemann surface and you can rotate it and see it in 3-dimensional Riemann surface projected on a screen. So take a couple of functions of your own choice, different from everybody else, and construct Riemann surfaces for this function. So the function needs to be multi-valued on the complex plane and single-valued on a Riemann surface. That's the definition of Riemann surface. And see how exactly it looks like. I think this would be a very nice exercise to grasp the idea of Riemann surface. So yeah, so I guess I'm done with essentials of analytic continuation. So what did we learn today? We learned analytic continuation on several levels. So first of all, one point was that we can exploit analytic properties to solve differential equations. And what we did today, we exploited the property that a real and imaginary parts of analytic functions are harmonic functions. So it means that if you ever need to solve Laplace equation in 2 dimensions, then you can replace this problem by a problem of finding analytic function on the complex plane with the same boundary conditions. These 2 problems are intertwined, or essentially boils down to the same problem. Therefore, all problems of Laplace equation in 2 dimensions, such, for example, as finding eigenfrequency of drum. You have a drum that oscillates, drum of a particular shape. You want to find spectrum of this drum. You want to find its eigenfunction. It's the same as to solve Laplace equation with the boundary condition on the edge of this drum. It's by construction analytic function. Other set of problem, 2-dimensional hydrodynamic flow also can be cast as a problem in complex analysis. Maybe Yoni will give you more examples on that. Another point that we made today was that if you have a function that is given by a converging series within a domain, we can analytically continue this converging series outside of domain by procedure which is called analytic iteration. So we're essentially saying we are looking at this function as a function of a complex parameter on the boundary, and we extend the definition of our function by analytic continuation outside of the boundary of the domain. And this is how many very important functions, such as Riemann functions, are defined. That was the second point. And finally, we discussed analytic continuation of multivariate function. And we saw that the natural way to do it is via Riemann surfaces. So this is how this very important fundamental object of modern mathematics arises. You can associate with any multivariate function its Riemann surface. And on the Riemann surface, a multivariate function becomes single valued. That's very nice. So I guess that's more or less all what I wanted to tell you today. And the next subject of our lecture will be conformal mappings.
Okay, that's it.
Yes, that's it.
Thank you.
Okay, so people, do you have people online? Do you have any questions?
תודה רבה.
בבקשה. Okay, so we end this meeting.